The topic of this video is the quantum mechanical rigid rotor, or particle on a string. And I'd like to start by talking a little bit about why we're studying the rigid rotor. First of all, this model describes the rotational energy levels of molecules, anything diatomic or larger in the gas phase. Or in the vapor phase. And this rotational energy that the molecules have, they can be occupying these various rotational energy levels, and this rotational energy contributes to the heat capacity and thus to the thermodynamic properties of gases in general, since the heat capacity is related to things like the enthalpy and Gibbs free energy of a molecule. The other topic related to the rigid rotor is the rho vibrational IR spectrum, in that in the infrared, particularly in a high resolution infrared spectrometer in the gas phase of vapors like HCl vapor and so on, you're going to see rotational transitions sort of superimposed on top of the infrared spectrum. And the combined spectrum is called the rho vibrational spectrum. And the rotational part is modeled using a rigid rotor. Similarly, in addition to the infrared spectrum, it shows up in the microwave rotational spectrum. So the rotational transitions are lower in energy. The difference between the rotational energy levels is smaller, and therefore they can show up as sort of splittings between lines in the infrared spectrum, where there's a combined transition involving a change in the vibrational quantum number and the rotational quantum number, or there's the pure rotational spectrum in the microwave region of the electromagnetic spectrum. And what may seem a little unexpected is that the solutions to the rigid rotor are essentially are related to the H atom, and in particular things like angular momentum in atomic energy levels is handled using the solutions to the rigid rotor are actually just sort of brought over to deal with rotation, the angular momentum component of electronic motion in atoms. And of course that ultimately relates to the orbitals, the shapes of the orbitals. And of course, those atomic orbital shapes are going to be important for covalent bonding as well. So really, the rigid rotor, extends all the way through chemistry, up through bond, including such crucial aspects of chemistry as covalent bonding. So now that we've sort of motivated why we want to study this rigid rotor, now let's consider the physical picture. And we start with a particle on a string picture. So we've got some tether, or could be, we think of it as a rigid tether, or we can think of the tether being held taut by the centrifugal force, and we have some particle of mass m. It's moving with some momentum p, and there is a distance r between the fixed point and the body that's rotating. And you may recall from college physics or university physics that angular momentum is a vector quantity. And the angular momentum of a rotating system, a particle on a string, is r cross p. So we can think of the distance there in our diagram as being denoted by big R. But we can also use little r to talk about the actual vector directionality that gives us r cross p, where we have a cross product. And another concept from angular momentum is moment of inertia. And if we have a particle at some distance r, moment of inertia is mr squared. Inertia. Okay. And so then we can, this is for one particle. So that's basically some concepts from classical physics. And we can, that's for a single particle. If you have multiple particles, you can calculate moment of inertia about a certain point by adding up the masses and the squares of the distances involved. We can, and cross product. We'll talk about cross product more later. One thing that I wanted to say quickly about cross product, if you think about, say, rotational motion in the xy plane, that's going to give rise to angular momentum vector pointing along the z-axis because of the way that cross products work and the way that angular momentum is defined. And so if you have a bicycle wheel rotating, it has an angular momentum. That angular momentum is pointing along the wheel axis, in one of the directions. If we have, and of course, we have to keep in mind the right-hand rule. Which is that if we have say, counterclockwise motion in the xy plane, then the angular momentum is going to point along the plus z axis. If we have clockwise motion, then it would be pointing along the minus z axis. Now we can expand from one particle to two particles by using the center of mass coordinates. So changing to the center mass frame. So if we have two masses, M1 and M2, and then you have rotational motion about the center of mass, and those two, we're not going to worry necessarily where exactly the center of mass is right now. That, of course, can be calculated in a straightforward way. But you would have rotation about the center of mass, which is maybe let's say here, or if M1 equals M2, it would be right in the midline, and you would have this kind of rotational motion about that center of mass. And in this case, you can still treat the system like a one-body system if you redefine, if you use a reduced mass, and then your then your moment of inertia is mu r squared, and of course mu is equal to m1 m2 over m1 plus m2, as we saw previously for the for vibration and the diatomic the vibration of a diatomic molecule. And let's see, the overall magnitude of the angular momentum, which we'll denote using vertical lines here. It's sort of the length of that vector is given by P times R. And that's just not telling you the direction that it's going, just the overall magnitude. And the kinetic energy for this case, or for the previous case of particle on a string about a fixed point, the kinetic energy is L squared over 2I. And you can see that if L is defined as PR, that and I is mu r squared, that or mr squared in the case of a single particle rotating about a fixed point, that when you can rearrange and you'll get p squared over 2m, and which we know is kinetic energy of rotation. And the next issue is, what is the potential energy in the system? The potential energy is, which we usually use the symbol capital V for, is going to be zero. There's no potential energy associated with this motion. Now, there's some restrictions on the motion, but the forces associated with sort of holding your molecule together are acting at right angles to the direction of motion, and therefore there's no potential, because there, in order to integrate the potential, there's a dot product involved of the force and the motion. Okay, the next thing we're going to have to do is, so we know roughly what our kinetic energy term is, although this isn't quite a complete expression, as we'll see, the L squared over 2I. It's useful in some cases, but in other cases it can be limited. It's not really giving the kinetic energy in terms of the full x, y, and z, or r, theta, and phi coordinates. And so it turns out that we can't really solve the rigid rotor problem in 3D in Cartesian coordinates, so we have to switch to spherical coordinates, spherical polar. And that will allow us to develop an expression for the kinetic energy in terms of angles in spherical polar coordinates. So let's introduce spherical polar coordinates. We've got our three Cartesian coordinates, x, y, and z. And then we have some vector kind of pointing out, hanging over the positive quadrant of the xy plane, just because that's a convenient place to have it sticking out to help us define our angles and so on. And we have some distance r. And we can project this vector onto the xy plane, and the angle between the x-axis and the projection onto the xy plane, we'll call that phi, and the angle with respect to the z-axis, we'll call that theta. And so the basic problem here is to go from x, y, z to r, theta, and phi, and relate these quantities. And again, yeah, let me just write out that theta is the angle with respect to the z-axis, and phi is the angle with respect to the x-axis of the projection onto the xy plane. Okay, and then we can come up with some relationships based on trigonometry here. Phi is going to be the arctangent of y over x. Theta is going to be arc cosine z over r. Another way to define things is you can define x, y, and z in terms of r, theta, and phi. So z would be r cosine theta. X is r sine theta cosine phi. And y is r sine theta sine phi. And I'm not going to go into the trig too much there. I'll let you look at that. Another thing that we'll need is in the case of integrating, and I encourage you to look at other sources for to help explain spherical polar coordinates if you need more of a review. Our differential volume element in Cartesian coordinates is dx dy dz. In spherical polar coordinates, if we differentiate these expressions and do some rearrangement, we end up with dx dy dz is equal to r squared dr sine theta d theta d phi. And so this r squared and so on end up being important in some cases. We have to include this as our differential volume element in when we do integrations of wave functions, say to normalize a wave function in spherical polar coordinates. Now the other thing that we need to think about is our going the other way. So for integrating, we need that. For differentiating, we need our del squared, our Laplacian in spherical polar coordinates. So in Cartesian coordinates, it's d squared dx squared plus d squared dy squared plus d squared dz squared. However, in spherical polar coordinates, and this takes several pages to derive, we'll just use the expression standard result, which in spherical polar coordinates is that we get 1 over r squared d dr r squared d dr. And so when we actually act this on some function to the right, we're going to first take the derivative with respect to r. You act the sort of rightmost expression on the system first. So you take the derivative with respect to r, then you take the result of that, right, which is going to be some function, and you multiply that function by r squared. Then you take the derivative with respect to r again, take the result of that, and then divide by r squared. So there's this there's this sort of angle of attack or direction of attack that it's the rightmost derivative that gets acted first. Okay, and that's one term. That's the radial term, and we get 1 over r squared sine squared theta d squared. D squared d phi squared plus 1 over r squared sine theta d theta sine theta d theta. And again, you have to consider this order of attack. It ends up being more important in the theta term, as we'll see the derivatives with respect to r drop out in the rigid rotor, but not in the case of the H atom. So now that we have our Laplacian in spherical polar coordinates, our Hamiltonian, there is no potential energy, and our Hamiltonian is the Laplacian term, the del squared term that represents kinetic energy plus the potential energy term. There is no potential energy in this system, so our Hamiltonian H is minus little h bar squared over 2 mu del squared. And why do I say 2 mu? Oh yeah, it's mu because we're dealing with reduced mass. Okay, so then if we sort of combine these, first, big R is fixed. So the derivative, the first term, the sort of first set of derivatives with respect to R drops out because our distance is fixed. It's a rigid rotor. That's the way we're defining this problem. And that's because it's not that there can't be motion along the internuclear coordinate, but we sort of already handled that with vibration, right? So we're taking a divide and conquer type approach, treating them separately. Now they can couple. That's another issue that we probably won't deal with directly in this course. The other thing that we can notice is that I equals mu r squared, and all of these other terms in our del squared have an r squared in the denominator, and then there's this minus h bar squared over 2 mu out front of the del squared, and so we can do a substitution there and use I instead of r squared, so that we won't even have r explicitly in our Hamiltonian. So then our Hamiltonian, in terms of just the angle, the important angular parts, is minus h bar squared over 2I. And again, we can pull all the r squared out of the denominators of the various angular terms in the derivative, and we get minus h bar squared over 2I, and we get 1 over sine theta d theta sine theta d theta plus 1 over sine squared of theta. Or you can use parentheses around sine theta and use parentheses to square it. Let's say then d squared d phi squared. Okay, so this is still, fairly messy, but this is what we end up with. This is the Hamiltonian for the rigid rotor in spherical polar coordinates. Okay, and we're not going to derive. It turns out that these second order differential equations in spherical polar coordinates, show up elsewhere in diffusion, in optics, and so on. And so it turns out the solutions to this differential equation are known, and they are a set of functions, a set of sort of special functions known as the wave function solutions to the Schrodinger equation are what we call the spherical harmonics. And we're going to write them as follows: YL comma M, and they are functions of theta and phi. Now they're often written with the L up in the sort of superscript of the Y and the M in the subscript, but I find that confusing because sometimes we have to square the YLMs, and so there's an ambiguity there, and so I'd rather just keep them both in the subscript where they're not confused for sort of squaring the wave function, that sort of thing. So I prefer to keep the quantum numbers in the subscript, but you'll see both in the literature if you look things up online and so on. These are also called Legendre polynomials. Named after the French mathematician slash probably physicist. And we won't worry too much about what those look like right now. We'll talk about that later. We're going to instead talk about what happens when we act the Hamiltonian on our YLM. And sometimes I forget the comma there, but I'll try to remember. So we act our Hamiltonian, which is a derivative with respect to theta and phi on our YLMs that are functions of theta and phi, and we get back some energy, which it turns out actually depends on L. So that's our Schrodinger equation, h psi equals e psi. In this case, the psi is this, the wave function is this spherical harmonic. That's the instantiation, right? When we put the details of this system in, we call that particular wave function a YLM. And again, it shows up in other equations. And then the expression for the energy is L, and that's supposed to be an L, script L times L plus 1, h bar squared over 2I. So, so h YLM equals L times L plus 1 times h bar squared over 2I times YLM. So it's an eigen, so these YLMs are eigenfunctions of the Hamiltonian, and these are the energy eigenvalues. And the other important thing is that L is a quantum number, and we use this sort of script L, and it actually starts at 0. It's an integer that starts at 0. So those are the allowed values of L, the angular momentum quantum number. And there's a second quantum number, M, and sometimes called M sub L, so that you don't confuse it with mass, and so that you don't confuse it with the M quantum number that shows up associated with electron spin. And ML is minus L. It ranges from minus L to L. And this is the magnetic quantum number. I believe some places it's called the azimuthal quantum number. And basically it's telling us something about the direction of rotation. So the L quantum number is sort of telling you how much rotation there is, and the L quantum number is telling you what rotation and what in kind of in what planes is involved. Okay, and the M quantum number doesn't affect the energy. So we'll see again for this system that there is degeneracy. Now there's a restriction here in that M always has to be in the range of minus L to L. So you can have like Y, you can have a YLM that's Y10, right, where L equals 1, M equals 0. You can have a Y11, you can have a Y1 minus 1, but what you can't have is a Y0, 1, or a Y0 minus 1. You can have Y0, 0, it turns out, right, from looking at this. And let's move on to actually looking at the functions. These end up being polynomials in involving sines and cosines and maybe complex exponentials. So the y00 is a very simple function, 1 over, it's just basically a normalization constant, 1 over 4 pi to the half. And this corresponds to basically a spherical wave function. And the y10 is it has a normalization constant out in front, 3 over 4 pi to the half cosine theta. So it doesn't have any phi dependence. It's invariant. You can it has the same value irrespective of whatever value phi has. And this, because it has cosine phi, or cosine theta, and theta is the angle with respect to the z-axis. So this is maximum along the z-axis. So it max at x and y equals 0. but it's also going to have a theta ranges from 0 to hold on, let's see. I actually skipped that. Yeah, theta ranges from 0 to pi. That'll be something to think about. Okay, so then our y11 is 3 over 8 pi. And this normalization constant is not so important, right? It's going to be important in maybe calculating expectation values, but it's not so important for things like energy. Usually when I'm dealing with eigenvalue problems, I just kind of drop out the constants out front because that's the way the math works out. Okay, so y11 is sine theta e to the I times e to the I phi. And so these are, this is going to have a maximum in the xy plane, and you can think of it as kind of like a complex ring, sort of, or donut-ish shape in the xy plane. It's a tricky thing to try to draw. And the for the y1 minus 1 is has the same 3 over 8 pi sine theta e to the I, e to the minus I phi. And so those are the first few states, and we'll talk more about them later. A lot of times all we're interested in, though, are the sort of energy eigenvalues, and as we'll see, there's some angular momentum eigenvalues as well. And it turns out that these functions also help define the shape of the hydrogen atom orbitals, and which are then used, of course, for making the orbitals that are involved in bonding and so on. And so, so the shapes of these functions, as we'll see later, we'll do a little bit more modification of these functions, but we'll see that that they're definitely related to the shapes of the various sp and d orbitals in hydrogen atoms and in other atoms, and that form that are involved in bonding and things like that. Okay, so now let's see if we can break things down a little bit more and look at components of angular momentum. So it's a little bit difficult to visualize these functions. They're complex, they're three-dimensional, but maybe what we can do is we can break down what's happening with angular momentum and see which direction the angular momentum operators are pointing for these various YLMs, for these various spherical harmonics, and that'll give you some way to think about the rigid rotor, the sort of shape of the wave functions, or their behavior, their physical behavior through the angular momentum. So you recall that from the classical definition of angular momentum, L equals R cross P. It's a vector quantity, and it's given by this kind of determinant, where you have I, J, and K. Those are our unit vectors along the X, Y, and Z axis. And we put R, so first row is the unit vectors, second row is R, which is X, Y, and Z, and for a cross product, yeah, then you would, for the second argument, you would put in the next row Px, Py, Pz. And so that's going to be equal to Ypz minus Z Py along multiplied by our I unit vector plus ZPX minus XPZ J. So the way determinants work, right, there's you alternate the sign here, so so XPZ ends up with a minus sign in front of it, and ZPX does not. Okay, and so there's this, there's a sign flip. And if you don't know what I'm talking about here, yeah, definitely you can, I encourage you to, if it seems unfamiliar, take a look at the some sort of guide on Wikipedia or something to show you how these cross products work. And then the third term is the XPY minus YPX times the K unit vector. Okay, and so this neatly shows us what the three components are. Right, this component here, we can think of that as Lx, the component of the angular momentum along the x-axis. This would be Ly, and this would be Lz. And again, recalling our old right-hand rule, you can see that motion in the xy plane, right, would have non-zero quantities for x and py and y and px, and so that would correspond to positions and momenta in the xy plane, so motion in the xy plane, and that's what gives us Lz. And so that's a nice sort of check to make sure that we set this up properly. It jibes with our recollection of how angular momentum works, the sort of directionality of it. And so there's a couple of ways we can try to keep track of this. We can try to keep track of all three components. That's turns out not to be mathematically easy to do. And however, we can define the amplitude of L squared, which we'll just call L squared. So that's going to be Lx squared plus Ly squared plus Lz squared. And it turns out that that comes out of, we can pull that out of our spherical harmonics pretty easily. And we can think that this is the scalar length squared of the angular momentum vector, right? So if we think of angular momentum vector, this is This is its square magnitude. And that's often what we do with vectors in 3 space. We want to look at what is their magnitude, or what is their magnitude squared, right? That's often what you end up having to use if you want to normalize things to get a unit vector or things like that. So L squared is one thing that we will shortly come up with an expression for. It's going to take a little bit of work, some of which I'm going to skip. But we can use this classical version. Remember, there's this correspondence principle that says that if we want to know the quantum mechanical version of an operator, we express the classical version of the observable, and then you replace position and momenta with their corresponding operators, so that so the operators then, based on our classical expressions there, are going to be Lx operator is going to be minus I h bar y d dz minus z d dy. And there may also be, we can go from there to spherical polar coordinates maybe later when we need to. I don't want to go that direction right away. Ly is minus I h bar z d dx minus x d dz, and Lz is minus I h bar x d dy minus y d oops. Why did I put a z there? Okay, d dx. And that's based on the assumption that the momentum along the x-axis, its operator is minus I h bar d dx, and so on for the other directions. Okay, and then we can convert to spherical polar coordinates, starting from x equals r sine theta cos phi, and so on. And we get, some of them are kind of complicated. Lx is pretty complicated, Ly is pretty complicated. I might write them shortly. One of them ends up being very simple. Lz equals minus I h bar d phi. So that's nice and simple. And we end up using this one quite a bit, our Lz operator. In fact, it's related to our m, our magnetic quantum number. And for the other axes, I guess we might as well just, oops. You get this mess, sine theta, or sine phi, d theta, plus cotangent theta cosine phi d phi, and the other one, we're not really going to use these, but just in case you're curious, I don't want to make it seem like I'm hiding something. minus cosine phi d theta plus cotangent theta sine phi d phi. So those are much messier, but this LZ, very simple. And we know that our YLMs have these e to the I phi type terms. So it turns out that there's some math simplifies very nicely. Now our L squared, okay, let's think about this a minute. Let's see, oh yeah, it turns out that L squared, you can actually plug it in, but it's also, you can sort of pull it out of the Hamiltonian in that kinetic energy is L squared over 2I. And so you can, by inspection, you can figure out what L squared is from the Hamiltonian, because the kinetic energy is what the Hamiltonian contains. And so you can pull out L squared that way. And so you're going to end up with an expression that looks familiar, a minus h bar squared one over sine theta d theta sine theta d theta plus 1 over sine squared theta d squared d phi squared. So yeah, when you take Lx and you square it, and then you perform some simplifications and do the same thing with Ly and do the same thing with Lz, it boils down to this expression. And we can also get it by comparing to our Hamiltonian. An issue is commutation properties. And it can be shown, in fact, we probably will a little bit later show that the commutator of Lx and Ly is IH bar Lz. Sorry, that Z is not very clear. And Ly, Lz is IH bar Lx, and so on. And it also, so you can generate like if you know any two angular momentum operators, Lx or Ly, you can sort of generate the third from the commutator. And it turns out that here's a kind of surprising one: the commutation of L squared operator with the Lz operator is 0. In other words, they commute. And this has some important implications. If they commute, then that means that at least in principle, these are compatible observables, so that we can, at least in principle, measure them exactly, or we can at least do the math of representing the measurement exactly for both of these operators at the same time for the same wave function. In fact, this hints that perhaps, well, let's see, we know that our YLMs are eigenfunctions of the Hamiltonians, right? The spherical harmonics are eigenfunctions of the Hamiltonians, and the Hamiltonian is L squared over 2I. Well, 2I is just some constants, right, related to the reduced mass and the length of the bond. That's just the moment of inertia. So it turns out we have these YLMs are eigenfunctions of L squared. We'll see what the eigenvalues are in just a moment. And they're eigenfunctions of the LZ operator, which we saw here, this minus IH bar dd phi. And that you can see they're eigenfunctions just by a simple quick inspection. The L squared we have to do by perhaps more circuitous or indirect means. So so as it turns out, the YLM are eigenfunctions of the L squared operator and the LZ operator. And that's sort of hinted at by the fact that L squared and LZ commute. Or rather, the fact that they're eigenfunctions would dictate that they must commute, and they do. Okay, let's look at the eigenvalues of those operators. Actually, let's go ahead and stop this lecture now, and next lecture we'll talk about eigenvalues of the L squared and LZ operator.